Good evening and happy Thursday. Last evening, we looked at exponential functions and logarithmic functions. Okay, so we're going to continue looking at logarithmic functions by looking at the properties of logarithms. Okay. So we're going to say b is a positive real number not equal to 1. And then m and n are any positive real numbers. So the log of m times n is the same as the log of m plus the log of n. The log of m over n is equal to log of m minus log of n. Take the log of m raised to the p power. It is p times the log of m for any real number p. Log base b of 1, so log of 1 is always 0. If you take the log of its base, it's always 1. And log base b of x is log base a of x divided by log base a of b for any positive real number a. So this one here, this last one, it's called the change of base formula. The one that is typically used is to convert it to the natural log, right? So as an example, if you have a calculator that doesn't let you do general bases, you can just do natural logs. And let's say you were asked for log base 6 of 28, and I want an approximation to that. What you could do is in your calculator, you go natural log of 28 over natural log of 6. Right, and that's how you get the approximation. Some comments on notations. Right. This is understood that it's only the m being raised to the power. Right, it's not the entire log being raised to the power. We will often represent the entire function being raised to a power this way. I should say greater than or equal to. For non-negative powers. Right, and this is true even for functions, right? So if we take a function and raise it to a power, we will also represent it this way. So these are not the same. And again, that would be like this. Right. So this right-hand side here means it's the reciprocal of log of x, whereas this is the inverse of log of x, which happens to be e to the x, right? Same thing here. This is 1 over f of x on the right. The left is the inverse function of f. So what we're going to do is expand the following expressions using the properties of logs. Right. Another way you may have seen it, right, to right, may also be stated as writing the expression as a linear combination of logarithms. They mean the same thing. So for the time being, just go one step at a time. First thing we should notice is that there is log of a quotient. Right, so that is the difference of the logs, right? So it's the log of the numerator minus the log of the denominator. Then we notice, look, this term here, right? It's the log of a product. That is the log of the sum of the logs. And there would be the fully expanded version. Now, being able to do this is very helpful in Calc 1. In fact, there's an entire technique in calculus that revolves around these properties. Right? right? So does this one seem to fit any of our properties? So what is the product? It's what times what? Right, very good. So difference of squares, right? So it's x plus 1 times x minus 1. Which then becomes sum of logs. Now, is there any other simplification that can be done? Very good, there's not. So that'd be our fully expanded form. I'm going to take this one step at a time. First thing we notice, it's a quotient. Which makes it the difference, right, of the logs. If we take a look at this log here, it's a log of a product, right? That means it's the sum of logs Is there anything else we can do? And what is it that we can do? Which ones? Okay. Well, technically that's correct. There's a simpler way. Right, the power comes out as a constant multiple. Right? And the reason for doing that is if this is not a positive integer, if your power is not a positive integer, then your expansion wouldn't work, right? You can't do something like this and go, oh, well, that's x times itself half of the time, right? But the rule is still valid, right? So even if this here was a 1/2 instead of a 3, we'd still bring it down as 1/2 log. Okay, this one. There's a couple ways we could start. Okay. There are two ways we can go about this. The first is to recognize the square root. What power is a square root? That's the first way. Or we could recognize this as a quotient. All right, so I'll let you choose. Go to the link. Choose which path you want to go down, either path A or path B. One with the most votes is the one we will go down. And if there's a tie, I serve as the tiebreaker. I guess if I unmuted, huh? I said, next thing that we noticed is we had a log of a quotient. Right, that's where this step came from. Now we notice that this is a log of a product. Distribute that negative through. Is there anything we can do with this first log? No, there's only one thing left we can do. And let's distribute that 1/2 through to everything. Wait for this to catch up. There we go. All right. What do we notice here? So what are the terms that are being multiplied? Right. Is there anything else we can do? What is the base of ln? And what is the base of what we're taking the log of? Well, what's ln of e? You saying ln of e is 5x plus 1? Or are you saying that this whole thing is 5x plus 1? Log base b of b is always 1. Wouldn't that make the ln of e equal to 1? Right, so remember, it is, right? Because natural log is base e. The log and the exponential are inverses. Right, so what you're going to be left with here is just the power, 5x plus 1. Right, so the whole thing simplifies to 5x plus 1. Right, because the other way you could do it is what you originally did. Right, and write it like that. But then this term here is just 1. And so you're left with 5x plus 1. Right, both ways are valid. Now, there is something we can do if we make an assumption. If we know that C is a constant, then we could simplify this even further. We can just replace log of c with some new constant c1, right? Because if you take the log of a number, it's a real number, isn't it? Now you can't pull the +1 inside of the log. Right? But of course, now what we could do is we could also just write that as c2 plus 5x, right? Where c2 is log of c plus 1. Right? Because again, what's log of a real number? It's a real number, isn't it? If you add 1 to a real number, you still get a real number. Right, so this kind of manipulation can also be useful in calculus. But it is not required, right? I would be happy with this. Okay. Now what we're going to do is we're going to go in the other direction. We're going to be given an expression, and we want to condense it. In other words, we want to write it as a single logarithm. We can only do this if the logs are of the same base. Which, of course, for these problems, they will be the same base. Right? So the first thing that we notice is we have a scalar multiple, right? This first term. So we raise what we're taking the log of to that power. In this case, it's log base a of u cubed. Now we notice we have a difference of logs. Right? That is the log of the quotients. Right? First thing we notice, each of the three terms has a scalar multiple in front of it, right? Has a coefficient. One-third power. So how else could we write 5 to the 1/3? Because that just, it doesn't look right. Oh, I see. Now that we couldn't do. Right, so what's another way of writing 5 to the 1/3 power? Because again, conventionally, we don't ever write that. We could write it if it was x, right? We'd leave x to the 3rd power as x to the 1/3. But when it's a number raised to a rational exponent, we typically don't leave it like that. Yep, cube root of 5. All right. That's how I'm going to write the first term. Oops, why am I writing 4? Again, there are a couple ways we can proceed from here. Since what we now have is just sum and difference of logarithms, we could just work with this left to right. Right, so we could start by combining these two. Or we could notice that these two have a common factor. Right, they have a -1 in common, so we could also just factor out that negative. It honestly doesn't matter. So I think what I'll do is I'll start with the first two terms. But now we have quotient of logs again. I'm sorry, difference of logs again. Which makes it the quotient of the logs. Right? But this term here can be simplified. As such. Right? And again, we notice that we have some scalar multiples, right? So let's take care of that first. Now we work left to right. Right? Or again, doesn't matter. We can do it however we want. And it's work right to left to right first. Right? We combine these two terms. Now we have the sum of logs still. I forgot to write. Oh no, I did write. I just wrote in the wrong spot. We could leave it like this. Or I could simplify it. I could do that. Typically for variables, we don't. Right, so it's more customary to leave this as a 1/3 because it's x minus 3. But it doesn't matter, right? You could write it as the cube root of x minus 3. That's fine. I'm going to pull this x cubed inside. Wait. Do I actually want to do that? I don't think I do. Now that I think about it. Because if I do, this is how it's gonna look. Oh, that doesn't matter. That is entirely up to your preference. Of course, now that you mentioned it, I can't unsee it. Because I prefer to write it in descending order of powers. Right, so yes, I probably would write it as x plus 1 instead of 1 plus x. But again, that is a purely aesthetic preference. It is one way isn't more advantageous. Right. I would probably, now that I see it, I'd probably just leave it in this. Right. So there's two ways to proceed. Right. The first way we could proceed is by distributing the 1/2 through first. The second way is to simplify what's in the brackets first. So again, I will leave it up to a vote. You clicked on the right link. Because the first poll I posted, I closed already. And now this one's closed. Might be your firewall. So it may have just been blocked from opening external links. All right, the result that one was to go ahead and distribute the 1/2 through. All right, now we notice, of course, each term has a scalar multiple. All right, now let's just work left to right. Right, first two terms, sum of logs, right? So it's the log of a product. Now we have the difference of logs. Then we can leave it like that. Or we can recognize that every single term has a 1/2 power. So we can factor the 1/2 power out. Either one is acceptable. Again, it's, what's more aesthetically pleasing to you. All right, let's look at this one. All right. First thing that we notice, scalar multiples. Right? Now we notice we have a difference of logs. Which again, we could write this way if we wanted to. Is there anything else we can do? What do you mean put an E? Well, it's understood to have base E. Now, writing ln is the same as writing it log base E of x. There is still something we can do. So there are two things that you're always allowed to do in mathematics. The first is add 0. The second is multiply by 1. Isn't natural log of E equal to 1? So I can multiply by it without changing the value, right? Because anything times 1 is just itself. So multiplying by 1 doesn't change the value. Isn't this now sum of logs? is what one of the formulas? Where you lost? It's this property right here. Right, sum of logs lets us write it as log of a product. I can pull this e to the c inside by squaring it first. Right? If you take e to the 2c and raise it to the 1/2, it's just e to the c, isn't it? Right? So in general, what you can do is, let's say you have this, right? Let's do that. You can always pull this outside term in by raising it to the 1/n. All right, so it's kind of like the opposite of, right? So for instance, if you had square root of 8, that would simplify to 2 root 2, right? Because it's square root of 4 times 2, which is root 4 times root 2. But you can also go in reverse. Right, so that's what this is. Well, that's what this here is. It's just working in reverse. Again, not necessary. Yes. So the instruction said to write them as a single logarithm. So this was the goal. Are there any questions on the properties of logarithms? Okay. Moving on, we now look at equations that involve exponential and logarithmic functions. Right? Start with, 2 to the x equals 6. Well, the idea is the same. You want to isolate x. So you want to undo the exponential. How do you undo an exponential function? That's a power function. Log. Specifically, isn't this an equation in exponential form? So why don't we write it in logarithmic form? What would this equation be in logarithmic form? Not plus x, equals x. Hate it when that happens. There's your solution. Same idea here. Right? Now we have a simple linear equation. Well, they're very easy to solve, right? Add 4 to both sides. Then divide both sides. by 3. There's our solution. Now, of course, we're feeling fancy. We can simplify this. Remember, it's not 15 thirds. It's log base 2 of 15 all over 3. No, that can't be reduced. However, (16) is 2 to the 4th, so log base 2 of 16 is 4. The 1/3 scalar multiple raises each of 15 and 16 to the 1/3 power, so cube root. So we get cube root of 15 and cube root of 16, which is 2 cube root of 2. Which then combine to give you log base 2 of 2 cube root of 30. All right, so could also write that as your answer. Doesn't matter. I'd be happy with what's boxed. All right. So this one's going to take longer than 2 minutes, I think. So I think what we'll do is we'll just go ahead, take a break now. And then when we come back at 7:50, we will look at this problem. So I will see you all again at 7:50. Okay. Now here, notice we have different bases. Well, undoing exponential, you still use a logarithm. But since we're dealing with different bases, the question is, which base logarithm should we use? And the answer is, it doesn't matter. By default, we use the natural log. So we take the natural log of both sides. Now use laws of logarithms. Distribution. All right, move all of your x's to one side and all of your non-x's to the other side. Factor out an x. Make that arrow. There we go. All right, and now isolate x by dividing. I'm going to move this down. Right, and there's your answer. Again, you could get fancy. Right, and try to simplify this. Again, using the properties of logs. Right, 5 to the 4th power is 625. That would be the numerator. All right, denominator, we'd have 5 times 7 to the third, which winds up being 1,715. And then we could use the change of base formula. Let's write that. Log base 1,715 of 625 over 7. Okay. You might just be tempted to take a log of both sides here. Yeah, don't do that. Right? Because we have a difference. Right? And there's no way to simplify the log of a difference. So instead, why don't we multiply everything by a 2 to the x? So 2 to the x times 2 to the x. Isn't that 2 to the 2x? Right? And then 2 to the negative x times 2 to the x is just 1. We get 2 to the 2x minus 1 is equal to 2 to the x. Write this as 2 to the 2x minus 2 to the x minus 1 equal to 0. This looks quadratic. So to see it, we do another common technique in mathematics called change of variable. I'm going to replace 2 to the x with y. Then 2 to the 2x. Isn't that y squared? Two to the x is just y. And of course, 1 stays as 1. Y squared minus y minus 1 equals 0. We have quadratic form. And we know how to solve a quadratic. This cannot be factored, right? So we have to use the quadratic formula. And quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. We get y is 1 plus or minus root 5 over 2. But y, we said, was 2 to the x. Okay, so we're going to get 2 to the x is 1 plus root 5 over 2, or 2 to the x is 1 minus root 5 over 2. Can we have both of them? Now, here's the beautiful thing about mathematics, right? There is no maybe. Okay, you say no, so defend your answer. You're saying we can't have both of them. So which one can't we have? What do you mean the negative? Which one is negative? Right? 2 to the x can never be negative. Right? So that's ruled out immediately. This means the only possibility we have is 2 to the x is 1 plus root 5 over 2. Which means that x is log base 2 of 1 plus root 5 over 2. Log base 2 of 3x minus 4 is equal to 5. Now, again, we want to isolate x, right? So we want to undo this logarithm. Another way of writing it is we have an equation in logarithmic form. Why not write it in exponential form? Exponential form. Wouldn't it be 3x minus 4 is equal to 2 to the 5th? And 2 to the 5th is 32. Now we have a very simple linear equation. Add 4 to both sides. Divide by 3. We get x is equal to 12. What's the domain of a logarithmic function? Open or closed? This is the first time we're looking at an equation involving a function that is not all real numbers as its domain. We have to make sure that 12 is actually in the domain. Right? Well, 3x minus 4 would have to be greater than 0, meaning that x has to be larger than 4/3. Is 12 larger than 4/3? It is. So 12 is in our domain. So it is a solution. Let's just wait for this to catch up. All right. Here, what we're going to have to do is use the laws of logarithms. We have a sum of logs. Right, which is log of a product. We now have a equation in logarithmic form. We want this written in exponential form now. Wouldn't it be x squared plus 3x equals 10 to the first? Right, because we're dealing with the common log, which is base 10. This looks like it's going to be quadratic. Yes, I've written just log that is understood to be the common log, base 10. We can factor this, can't we? We're going to get x equals 2 or x equals -5. Why can't it be -5? Right? -5 is not in the domain of log of x. Also happens not to be in the domain of log of x plus 3. Right? But what's important is it's not in one of the domains. So it can't be a solution. So we have only one solution, x equals 2. It's still not a solution. It has to be in both. And specifically speaking, it has to be in the domain of every function that's involved. Are there any questions? Right. Now looking at models. Right. So a certain amount of money, P naught, is invested at an annual rate of interest R. How many years would it take for the amount of money to double if interest is compounded n times per year? This is known as the doubling time of the investment. Well, we start with our model, right? So it's the compound interest model. We want to find the time t it takes for P of t to be twice our investment. Right? That's P naught. Divide both sides by P naught. Remember, we're trying to solve for t, right? So we have to isolate t. Well, isn't t in the exponent? Which says we have to take a log. Conventionally, it's a natural log we take. And then we use law of logarithm to bring the exponent down as a scalar multiple. Now we can easily solve for t. And there's our doubling time. Another common exponential growth decay model is the idea of half-life. Right, so half-life of a radioactive isotope is the amount of time it takes for half of the isotope to decay. Right. Now, there are some problems with this. Half-life is more of an expected time. Right? Because this is all technically governed by the laws of quantum mechanics. So if we're given a certain amount of radioactive isotopes, in this case, I'm just going to work with what they give us. Say we're given a certain amount of a radioactive isotope that has a half-life of 35.2. In this case, let's say we're given a total of 5 grams. And we split it into 5 1-gram experiments. What we would find is that some of them, after 35.2 years, would have less than half a gram. Some of them would probably have more than half a gram. Right? You might even find some that have exactly half a gram, but that is probably not going to happen. That's That's pretty rare. Right. Because quantum mechanics is weird. We are going to obviously ignore quantum effects. And we're just going to assume that it will always take 35.2 years for half of the amount to decay. The model for radioactive decay. The amount remaining after a time t is A naught, the initial amount, times e to the kt. Since we're dealing with radioactive decay, our k is going to be negative. Positive k would represent an exponential growth. Negative k represents an exponential decay. We need to find this k value. Well, that's easy to do with the condition. We know the half-life is 35.2 years. I don't know why I wrote 0.5. I want 1/2. So we know that we're going to be left with 1/2 the original amount after 35.2 years. That means that 1/2 will have to be e to the 35.2k. Now, let me write this first. It means log of 1/2 is 35.2k, but log of 1/2 is negative log of 2. This means that our k value is negative log 2 over 35.2. Plug this k back in. But A naught is 1 gram, right? Oh, but using laws of logarithms and the fact that the exponential function and the logarithmic function are inverses, we can write this model as a of t is equal to 2 to the negative t over 35.2. We can now solve the problem. How long is it going to take for this 1 gram to decay to 0.01 grams? We want a of t to be 0.01. Write the equation in logarithmic form. We're going to get t is negative 35.2 times the log base 2 of 0.01. What I'm going to do is I'm going to show you how to use change of base formula. In case you have a calculator that doesn't do the log of a general base, right? You can only do natural log. So it was log base 2 of 0.01. So it'll be the natural log of 0.01 divided by the natural log of 2. And we get about 233.9. So let's just say 234 years. Decibel scale for measuring sound intensity is given by d equals 10 times the log of I over I naught, where d is the decibel level of sound, I is the intensity of the sound, which is measured in watts per square meter, and I naught is the intensity of the smallest audible sound, which is 10 to the negative 12 watts per square meter. First, we're asked to calculate the decibel level of a rock concert at an intensity of 10 to the minus 1 watts per square meter. Right? Be 10 times log of 10 to the minus 1 over 10 to the minus 12. Ten to the minus 1 over 10 to the minus 12 is what? It's 10 to the what power? So how did you get minus 13? Correct. You subtract them. So negative 1 minus negative 12. It is not negative 11. It would be positive 11, right? It's negative 1 plus 12. What does that log evaluate out to? What is the log of 10 to the 11th? So it's at 110 decibels. Now we're asked to calculate the intensity of a sound with a decibel level of 85. And that means 85 is 10 log of I over 10 to the minus 12. All right, laws of logs. Actually, did I have to do that? No, I didn't. Oh, well. I've already gone this route, so I'm going to stick with it. Right, log of 10 to the minus 12 is negative 12, right? And then negative 12 times negative 10 is 120. Which makes 10 log I equal to 85 minus 120, which is negative 35. So makes log I negative 3.5, right? Divide by 10. That makes I 10 to the negative 35, negative 3.5 watts per square meter. I think I'm just going to skip that last one. Are there any questions on anything we've done tonight? On what, the models? Or just logarithms in general? Yeah, modeling problems are always tend to trip students up. Because you have to read the problem, and you have to interpret what everything means and extract information, then actually write out your model. But you'll get the hang of it.